move to the next talk given by Dr. Harold Sung. Dr. Harold Sung is an assistant professor at NUS. He is recognized for his pioneering works in spiking haptic perception and spatial temporal haptic perception on the iCup robots. Personally, I was quite inspired by his research work from when he was at Imperial College. Harold, are you here?
Yep. Can you hear me?
Yep, great.
Okay, great. Can you see my
Fine.
screen? I just shared it. Is it coming up? Yeah. Okay, great. Okay, so thanks, Sean, for the very generous introduction. So my name is Harold, and I'm from the Collaborative Learning Adaptive Robots Lab, or CLEAR Lab, at the National University of Singapore in US. So what we do at the CLEAR Lab is that we explore, investigate the science and engineering of trustworthy collaborative robots. So robots that essentially we feel comfortable working with over the long term. What they translate to in kind of day-to-day operations is that we build machine learning models, we build theoretic decision, theoretic algorithms, and we apply these on robots. Okay, so we run experiments with real robots, as well as human robot experiments with people. We bring them to the lab in order to validate our models, validate our methods, as well as to gain inspiration and insights for new ones. So I can broadly kind of group the works that we do in kind of two broad areas. The first one is the cognitive affective area. Here we try to model essentially people. We try to model how they feel, how they think, and then we build models like computational models for human trust, where we see how whether the person would trust the robot to perform different tasks. We do things like intention prediction, as well as inversion reinforcement learning, this kind of thing. So I'm not going to talk about those things here. We'll focus more on the physical interaction bits. This is where I think the tactile perception aspects come into play. All right, so I think that to this crowd, I don't need to motivate the need for tactile perception. I think Sean and Ola give very great presentations showing why we need tactile perception. So I started working with tactile learning, as Sean was saying, way back when I was a PhD student, a decade ago now, at Yanis Demirci's lab at Imperial. And there we built one of the early models for basic incremental models for learning objects by touch, right? So learning to classify things using the iCup robot. And then we also did things like, try to see whether people learn incrementally from touch as well. And then, we showed that, yes, they do. Then I took a hiatus from this world of tactile learning and perception. The reason is that I had no access to tactile sensors for a very long time. But now, since I've started my faculty position in the US, I've booted up this particular research program again. So at ICRA in 2019, we started looking at whether we could classify textures using the iCup robot. And this was a joint work with my collaborator, Nguyen. In IROS, we started looking at whether we can use graph neural networks to count geometry of the taxels. And more recently, at this year's ICRA, we're looking at how we can combine vision and touch in a deep reinforcement learning. I'm going to focus on two particular pieces of work where we played around with these things called event tactile sensors. So if you don't know what they are, that's okay. I'll tell you about them. I'll tell you about, kind of the basic principles about how they work, what they're good at, maybe what they're not so good at, and how we can use them for robotics, okay? So the first work that I'll talk about was published in RSS last year. This was joint work with with a lot of people, but principally my PhD student TAS, as well as my collaborator Ben T and his team. So Ben's team, he's a material scientist and an electrical engineer, and he builds these sensors, okay? And how this collaboration works is that they will build a sensor, we will talk, he'll send us one, we will break it, or find out it doesn't work for our application, we send it back, and then this iterative process, and then we gradually improve the sensor to something that works well for a particular application. So let me start off by kind of describing what this event-driven or event systems are. So we'll use the example of the brain. So your brain is not like the GPU. Okay, it's not like performing a huge number of matrix vector multiplications every second. Okay, that's not what's happening. Your brain is composed of neurons, okay, which are interconnected in this large network. And these neurons are firing asynchronously and processing things called spikes. Okay, you can think of it little packets of energy. And so the neurons would accept spikes, and then once it reaches some threshold, they would generate a spike. So you can take this idea of asynchronicity as well as processing events, and try to create new kind of devices with them, like new sensors. So this is an example of an event camera. So it's easy to explain with camera because it's more visual. This is a scene where there's a cheetah running across. Okay, and if you use a standard frame-based camera, what you're going to get is you're going to get, let's say, 60 frames per second. You will get 60 images, right, of per second of this cheetah running across this this scene here. Now you notice that from frame to frame, there's a lot of redundant information. The sky is not changing, but you're still recording that anyway. Okay. Contrast that with the event camera. Now, the event camera, what's happening is that the pixels are firing asynchronously. So when the pixel intensity, if the intensity at that particular pixel changes by some appreciable amount, it's going to fire a spike. Okay, it's going to fire an event, whether positive or negative. Okay, and these are shown by these red and blue dots over here. Okay, so you notice that the spikes are being, or events are being generated at the region where the cheetah is moving. Okay, there are no spikes being generated at the sky portion where there is basically no change. All right. So why might you be interested in such a sensor? Because you're transmitting changes asynchronously, this can have benefits in terms of transmission, in terms of storage, as well as in terms of computation. So because you don't, you don't need to transmit the redundant information, you can have better savings there, as well as in terms of storage. And when it comes to computation, let's say I'm building a cheetah classifier. Right, I don't care about the background scene, right? I care when there's a movement in the scene, and then I can start zoning under that and kind of paying attention to whether that's a cheetah or not, and that can save me time when it comes to computation. So this can lead to low power consumption, higher temporal resolution because there's no central clock. Every pixel is firing asynchronously, as well as scalability because I'm transmitting only the changes. It's just redundant information which is flowing across my channel. So we've designed a neuromorphic tactile sensor, okay? And this is, it's bio-inspired, so it's kind of like a finger, okay? It's even about the same shape. So this is a 3D printed bone. There is a graphene-based pressure transducer and an EcoFlex covering for skin, and the taxels are arranged in this like radial pattern over here. Okay, so the question is, what do you see when you look at this kind of sensor? What kind of data does it generate? So I'm going to show you. This is our robot arm, okay, Frankie. She's going to pick up this soy milk carton over here. And this robot is equipped with two new touch sensors, okay, our two event sensors here, as well as a event camera. This is the prophecy event camera, okay? So I'm going to play this video twice. Maybe we'll look at the visual spikes first, and then after that, we'll look at the tactile spikes. All right, so here he goes. As the gripper is closing, you can see the spikes generated by the camera, and then here comes the lift, okay? So let's see that again, but now I'll kind of draw your attention to the tactile input. So tactile, as you might imagine, the data doesn't come in until there's contact here, and then here comes the lift. All right, so you can see distinct firing patterns, right, corresponding to different phases of this grasp and lift. All right, and the question we have is, can we make sense of this kind of data to do something useful with the robot? So we're going to do a visual-tactile learning. So we're going to combine information from the vision modality as well as the tactile modality. And we are kind of the overall architecture is something that you might have seen before. We have like a vision expert and a tactile expert that the information from that is combined, passed to some task-based neural network, and that generates the output spikes. So let's look more into detail. How this is different from maybe something you've seen before in the deep learning literature is that the neurons themselves are not they're not ReLU for a particular work. So if we decide to go with, if you have an event-based sensor, let's try event-based learning as well. Sorry, event-based kind of perception as well. Okay. So here we have spiking neurons. So they operate on similar principle whereby spikes come in, they increase what we call the membrane potential. This is, you can think of it as internal energy. Once that breaches some threshold, you're going to generate some output spike. Okay. All the energy is expended to generate this output spike, and then there's a refractory period after that. Right, so that's the idea behind this spiking neural networks. Now, once you have the model, you can train these in different ways. We decide to do approximate backpropagation. So if you want to train things by backpropagation, you need kind of loss function. So that's what we need to specify next. Now, you can't really apply, cross entropy here because the network is not outputting like real values. Okay, it's outputting spikes. All right, so the way to do classification is via something called spike count loss. It's very straightforward, actually. Let's just say we're trying to classify slip, okay, whether the object we're grasping is slipping or not. We have two output neurons. One neuron saying this object is slipping. This neuron saying no, the object is not slipping. Now we would specify for the output that's for the output neuron that for the slip case that if the object is slipping, I want this neuron to output maybe 100 spikes within a certain time period. Okay, and that's my desired counts. Okay, over here. I would also then run the data through the model and actually see how many counts are generated. This is my obtained counts. And I just take the difference between the two. All right. And that gives me my error. And then from the error, I can do approximate backpropagation into to train my model. Okay. So this works relatively well. A problem is that there's no way to incorporate any temporal characteristics into this loss. So it's only based on counts at the end of this period, right? So this is a problem when you want to do things like a slip classification, where you might be interested in classifying the slip as early as possible. Right now, there's no way to kind of constrain the model not to do that. I might decide to push all the spikes only towards the end. All right. So what we want to do is classify things as early as possible, and this is not possible here. So what Tas proposed, my PhD student proposed, is to incorporate a simple weighting function. So he changed the loss function in a very small way, but one that results in appreciable change in the output, as we'll see later. So here the idea is very simple. We are just going to weight spikes depending on when they arrive, okay, when they appear in the outputs. So if they appear earlier, we might upweight them. If they appear later, we downweight them. Okay, very simple idea. And so let's see how this works. So now we have our sensor, we have our model, we have a way to train the model with data. How does it? Does everything actually work or not? So I'm going to describe two experiments. The first is a container weight experiment where we try to classify containers weight. Next one is a slip identification. Right? There are comparisons with standard like deep neural networks in the paper. I refer you to that. I won't cover them here due to time. I suffice to say that the model performs relatively well compared to 3D convolutional neural nets as well as GRU-based models, but it doesn't perform that well compared to like the really state-of-the-art stuff like ResNets, for example. But those are really huge networks. So we're going to instead focus in on this in line with the theme of the workshop, the combination of vision and touch, all right, and seeing whether can you do well with just one of the modalities. You actually need both vision and touch. And the experiments are kind of designed in order to exploit the combination of the two. So let's do the container and weight classification. The goal here is to classify not only the container, but its weight as well. And I'll talk a little bit about that in a second. Just want to say here that the data is generated by using the kind of setup that you saw before in the video, where the robot would approach the object, close its gripper and then grasp and then lift it, okay, and hold it. And we only use data from the portion from the grasp to the hold, okay, for the experiments. So here we have 4 different containers: coffee can, a tuna can, a soy milk carton, a soda bottle. Most of them are opaque. The only one which is not really opaque is the soda bottle. We can actually see through it. And then we filled them with different amounts of liquid. Okay. For the tuna can, we actually use rice because we were afraid of the water leaking out, which is a big problem for robots. So that one had rice. The rest of them had liquids. Now, with this data set actually available online, if you want, you can go to my website, have a look. And there's the data set that we have online as well has expanded item. Is expanded, so it has more items in there, which mainly drawn from the YCB data set. So let's look at what the results look like if we were to do this. On the x-axis, you see a time, all right, how the model is doing across time. And the y-axis is the accuracy, test accuracy. Higher is better. Okay. Now let's look at vision. So as the gripper is closing, it's kind of creating small movements. And since the camera is mounted on the arm, the camera is moving as well, and so it's able to see some features from the scene. Okay, so the object that's about to be grasped, and that's why it's able to kind of give some early information about what that object is. Now, tactile information doesn't arrive till you don't see any tactile information until contact is made with the object. That happens about 2-second mark. Okay, and that's when you start being able to classify what kind of object is by touch. Okay, now you look at the combined model. Now the combined model does achieve better accuracy at the end, but the temporal profile isn't very attractive, right? What we would like ideally is that it would kind of follow the vision vision profile at the beginning when the visual information is coming in, and then after that, as tactile information starts flowing in, it's able to incorporate that into its classification. But that's exactly what you see when you use the weighted spike count loss, right? Because you're able to use this temporal weighting, you can encourage the model essentially to make classification earlier, and that encourages then the model to follow the profile that we described before. Okay, so let's move on to the second problem, which was slip classification. So here the object on the left is stable, and the object on the right is slipping, as you can see. They're actually the same object, okay, except that we induce slip by putting a little small mass hidden in the right leg. Okay, and that's how we induce slip in the right object. Now, the reason why we're using the same object here is because we didn't want it to be, immediately apparent from vision which one of it would slip. Okay, and we could attach these object markers as well, so they give us a quantitative estimate of how much the object is slipping. So in applying our models again, if you use the standard spike count loss, what you notice is that actually tactile information now plays a greater role earlier on, okay, because you can feel little movements in the object as you're lifting it, and that is indicative of slip. Whereas it takes a little while longer for the visual models to catch up, okay? But at the end, because a lot of vision, it's very clear by the end, whether the object is slipping or not, the vision-based model is able to classify very accurately whether the object has slipped. Now, but if you combined, kind of use the weighted spike count loss, you see now the combined model. Before this, the combined model kind of tracked the vision model, which is not ideal. But if you use the weighted spike count loss, now you see a nicer profile where it kind of uses the tactile information early on, and then it incorporates the vision information as it becomes available. Now, we also ran this slip calculation model on neuromorphic hardware. So this is specialized hardware for running these spiking neural networks. So thanks to Intel for giving access to their compute cluster. And here you see that not here actually, you can't see that, but the performance of the model, whether you run it on NVIDIA RTX, at that point in time, still the art GPU, and Intel OE chips about the same. They both achieve perfect accuracy by the end of the period, but and with equal latency as well. But the power consumption, when you run it on the Intel OE, is much less. In fact, it's more than 1,000 times less power, which is I think will be important for mobile robots, as well as robots kind of small, where battery and power is a concern, as well as embedded systems. All right. So I hope now you get an idea about what this event-based tactile sensing is, how it works, and some of the things that you can do with them. All right, let's move on to a second piece of work, which is more preliminary. Okay, this is work in progress. Again, with my student task as well as Ben and his team. And here we are interested in this problem called extended tactile perception. Okay, so what is extended tactile perception? So human beings have this remarkable ability to sense the world through other objects and through tools. Okay, so it's not when you're picking up a tool to use it, you're not interested in, sometimes you're not interested in like the properties of the tool, but you're interested in the properties of the object that the tool comes in contact with. All right, you're interested in the location of that object, or maybe whether the object's hard or soft. So that's kind of what we were trying to investigate here. Now, there's this nice experiment described in a Nature paper back in 2018. I'll talk a little bit about it because it's kind of cool. Now, you notice that this human participant over here is dripping this rod, okay, and she's going to lower the rod, okay, until it makes contact with this bar. All right. Now, what this participant is trying to do has to identify where on the bar did the contact come did the rod make contact with. All right, so for example, if it's here, they just should indicate it on the iPad here, right around here. The problem is that the person can't actually see where the contact took place. There's a barrier here, so they can't see it. They can't hear it either because they're here wearing these headphones, probably noise canceling headphones like the ones I'm wearing. So they can only kind of determine the location via touch signals or tactile information that they receive from their hands. Okay. So surprisingly, human beings can do this very well. Okay, they can do this, detect essentially where the contact occurred on this rod. It's as if the person has virtual tactile sensors, right, along the rod, even though obviously they don't. Okay, what they do is they only have tactile sensors on their hands. So the authors also propose a mechanism by which this occurs. Essentially, the location of the contact is encoded as mechanical vibrations that travel up the rod. And then based on and that is detected by the mechanoreceptors in the skin and encoded further as spiking patterns. Okay, and by examining the population level firing patterns, you're able to decipher the point of contact. Okay, so great. This is human beings. And we thought, you know what? I bet robots can do this too, right? I think robots can do this. So what we have is we have a kind of a similar experiment whereby the robot is gripping this rod, okay, this acrylic rod, and we are tapping different positions on the rod, and this generates some vibrations that travel up. It's picked up by our dynamic tactile sensors, okay, and that is then push through some signal capture to do some feature extraction, so your typical like machine learning stuff in order to predict a tap position. Okay, so here we've used two kinds of dynamic tactile sensors. The first is the new skin, which is an updated variant of our new touch. So the key differences are basically that it has a more regular kind of taxel pattern, as well as higher sensing. So we bumped it up to 4 kilohertz. We also played around with the biotech hydrophone sensor. So not all the sensors on the biotech, just the hydrophone sensor. So you can think of this as a one taxel dynamic tactile sensor. Okay. So instead of just looking at tap localization, which I think is an interesting task, but maybe not interesting enough, we also looked at grass stability, whether you can detect whether grass was stable or not when during robot-human handover, as well as whether you can identify foods using a fork. Okay, so I won't talk about the grass stability due to time. I'll focus on the localization and identification task. So for tap localization, the key problem is, can we identify the contact location? All right, you can see this as a one-dimensional regression task. Where we have 3 different rod lengths, 20 centimeter, 30 centimeter, 50 centimeter rods. And for each of these rods, we would, kind of tap the rod 1,000 times. And we say I actually mean Tas and Shui Song, who's a PA master student, the students who were working on this. And the ground truth is provided by OptiTrack, okay, markers attached to the human's finger. The next kind of problem is identification through a fork. So previous work has actually shown that you can identify, food properties through forks, but the forks that they use are specially designed tools. So accelerometer is attached to the fork and modified in some way. Here we're using a standard fork. Okay, we bought this fork from IKEA. All right, so standard off the shelf. You're just detecting the tactile information based on the tactile sensors that we have and the mechanical transients that flow through the fork. You can see this is a classification task. So there's 7 different classes here. There's a control class, which is nothing, a bowl of liquid, water, and then some food items. So tofu, watermelon, apple, green pepper. And for each one of these food items, then we would skewer each item 50 times. All right. So we had a few questions that our experiments were designed to answer, and I'll take each of these in turn. All right. And the first one is, can the robot localize context? And, there's a wall of numbers here. I just ignore the wall of numbers. Essentially, I'm going to summarize it for you. The answer is yes. Okay. And to a surprisingly good degree. So the lowest errors were about 1 centimeter on a 20 centimeter rod. Okay. And the errors for 30 centimeters was about 1 centimeter as well. 50 centimeters, about 3 centimeters, which is surprisingly good considering all we're doing is, we're kind of gripping on one end of it and trying to detect where the taps occurred. The next question you might have is, how fast do we need to sample in order to make such accurate classifications or predictions? So it turns out about 2 to 3 kilohertz. So I'll focus on the new skin results. Here you see on the x-axis log frequency, and here on the y-axis you see the error. Okay, so lower error is better. Now, as you increase the frequency, that creates a marked drop, right? In the beginning, really a fast drop in the error. But after some point, there's really not much improvement left to be had. Okay, so there's diminishing returns in terms of how fast you need to sample. So about 2 to 3 kilohertz seems to be a kind of sweet spot for this particular problem. So the next question you might have is, okay, do we actually need multiple taxels? I mean, maybe you do need one taxel is enough to do this problem and to solve this problem. And it turns out no, at least from our experiments, the new skin, when we use 2 fingers, so 80 taxels, we're able to do much better than the 1 finger new skin, which is 40 taxels. And then compared to the biotech, we're doing better as well. And the biotech, you can think of the single-taxel version, especially on the 50 centimeter rods. Now you can compare that also to single-taxel models. So here what we did was for the new skin, we would train a model for each one of the taxels and then compare that against the 2 finger and 1 finger versions. And you can see here that none of none of the single-taxel models actually achieve the same error as the ones that use multiple taxels. Okay, so let's look at the higher level task, which is, can you identify food via fork? And the answer is surprisingly yes, 90% accuracy. In fact, I was very surprised that the model was able to classify water to such a good degree. I didn't think it was able to do so, but yeah, it was sensitive enough that when you touch the water, it creates sufficient information in the tactile information in order for it to make this classification. And the errors are, I would say, reasonable as well. So when it got it wrong, you wouldn't think that it's an apple or a pear or anything, apple or pepper. It would say that it's probably empty, right? Nothing's there. Okay. And if you look at the apple and the pepper, this is the other kind of misclassifications. One is the other, and these two have similar kind of texture and consistency. All right. Okay, so I think that this aspect of tactile sensing, the fact that mechanical transients are there, can really help us design or get robots to perform much better when using tools, all right, to be able to sense the world via held objects. And I think there's some early work done in this area, but I think this work, I'm quite excited about this, because I think that this can lead to better methods for tool use. Okay, so that's this piece of work. If you're interested in this work or any one of the others, please head over to our website. We are, I'm very, or come talk to me. I'm happy to talk more about them. I just want to end off by discussing a little bit what I think are some trends and opportunities in this area, given that, that's the kind of theme. The first thing is that when I was a PhD student, I not only worked with the iCup, I worked with wheelchairs as well, smart wheelchairs for children, okay, to help them get around safely. And something I really wanted to do was to wrap the entire thing in skin, okay, not only on the on the bars and everything to detect collisions, but also on the chair, so that to detect posture and things like that. But the technology wasn't available then that allowed me to do something like that. But thanks to pioneering work from Gordon Chang's group and others, we're seeing that this is finally becoming something that I can do. So I'm looking forward to kind of wrapping maybe the fetch robot in skin, right, sometime down the road. I also think there's challenges in integration. So by integration, I not only mean kind of at a hardware level. So hardware level integration is quite hard, because the wiring and so on and so forth, but also across the pipeline. So for all the way from sensing to perception to decision making, to actions, to learning, and then to control. So all these things can benefit from tactile information, and to integrate all these together, I think it remains very much an open question. The next problem, like putting on my machine learning hat, is data. So unlike vision, tactile data is harder to come by, because it's you can't just put a camera there and collect information. You actually have to go and touch something, which is kind of hard. So I was really happy to see Shan's work on simulation, because I think that's very cool. That's something that definitely should be done. I think there's a lot of gaps there, and there should be research in this area, especially when dealing with deformable and soft objects. I think that's really the challenge, because our models aren't very good, the simulations aren't very good, and the sim to gap rail is significantly larger. So I think there are multiple research challenges there. And finally, I'm really happy to note that there are a lot more sensors now than there was when I was a PhD student. Some of them are getting to a price point which is somewhat attractive. Okay, they're still expensive, but not as expensive as they used to be. And I think that sensor ability will really encourage adoption and people to incorporate tactile information into their robotic applications. So that's it. I mean, if you're interested in some of the tactile sensors that we have, as I showed you about, we are also trying to make our tactile sensors into a form which is robust and something that you can play around with. So if you're interested, do register your interest here. I can tell you right now, the robot sensors are not really robust yet. Okay, these are lab prototypes. Okay, they break and everything like that, but we're working hard to kind of get them into a form which is something that you can play around with. So I hope to ship out a beta box by the end of the year, maybe a Christmas present. But no promises yet. COVID is throwing a wrench into the works. Okay. So let me end off there. Thanks so much again for the kind invitation to speak today. I hope you learned something today and you find the work interesting. If you want to know more, please contact me or find out more on our website. Thanks.
Okay, thank you, Harold. I'm going to play this reminder music.
Oh, okay.
Okay, so as we are running out of time, so shall we have a quick question, and then you can answer the questions in the chat. There are quite a few. So okay. Knowing asks, how did you measure test accuracy over time?
Oh, so we would just count the output. Is quite simple. We know what the true class is, and then we would see the counts of the spikes generated by the neurons, and the one which is the largest is the winning class, right? It's the predicted label. Yep, and then we just take that and then you can compute that over the samples that we did.
Okay, great. Thank you, Harold. I think we have to move on. We have this gathered time space, so you can talk to people and there, and please check out the questions in the chat box. Yep, thank you. Okay, so